Okay, so this is class meeting 2. This covers modules 3, 4, and 5. So in these modules, we got into TensorFlow used together with Keras, couple of assignments. Okay, so the assignments that so far. Overall, everybody's doing quite well in these. I even have one or two who are at 9, maybe at 10 now. So if you want to, you can definitely do that. The two projects, I haven't released those yet, but I do have the Kaggle project ready. We'll talk about that next class session. So the next time that we meet, there's two projects, and we kind of hit those on each of the two remaining class sessions. So 1 to 3 are complete now. The assignments that are due before the next class meeting, and I'll take you through those and just give you a quick sort of overview of that. Basically a regression neural network, a k-fold cross-validation network, and a classification network. After that, we start to get into what neural networks are really good at and see some computer vision, time series, and other things. So module 3 talked about Keras and TensorFlow, and there's a lot of code examples in there. I'm not going to go through the individual code examples. I'll show you some code in the PowerPoint form, but just really showing you kind of what I think the highlights are and emphasize those. So I think this is pretty interesting, and you might not be aware of this unless you're looking at kind of the global deep learning sort of platform. But this is data that Google compiles, actually. Francois Chollet, if I'm saying his name right, the creator of Keras, pulls this and he updates it pretty well yearly. This is from October 2017, so it's pretty close. I update this in the class whenever it was something new, and it does change around quite a bit from one session to the next. So this shows overall popularity on GitHub. Now this includes issues being raised, so older, not used as much deep learning frameworks will probably not have as many issues. Now issues are not really bugs always. Often they're bugs on GitHub. Usually there are people posting, my code doesn't work, please help me. So that happens a lot. I think there was a statistic once that 90% of the TensorFlow bugs do get closed with them basically saying your code doesn't work, post it on Stack Overflow, we don't have time to help you. Now I have submitted, I think, 5 issues to TensorFlow to Google. One of them they actually fixed, it was really a bug. Another they said too bad, that used to work, but we're not going to fix it. So a breaking change, and then I think the others were all in that category. So I have actually gotten them to say, one, yes, we agree with you, that is a bug, and they did actually fix it. That was back in the I think the first semester I taught this class. So you see TensorFlow is at the top in terms of the number of people who have started, the number of issues reported, all these sorts of things, the number of forks. Second to TensorFlow is Keras, and Keras and TensorFlow really aren't competitors. They're both Google products. If you're using TensorFlow, you're probably dealing directly with the compute graph. I mean, I will use TensorFlow sometimes not even to do a neural network. I just need math done really fast, and it's very good for that. Caffe, if you have not seen that one, that's University of Berkeley. That was before TensorFlow and before industry started really getting into making their own deep learning frameworks. Cafe was sort of top of the heap. So I've done some Cafe. You see Cafe used a lot in academic papers and other things. ImaxNet is also pretty big. That's the Amazon. That's the one that works really well with Amazon and is supported by Amazon. Thano has been abandoned. It was kind of the original deep learning framework that was created by Jeffrey Hinton and crew and others. So it will remain on the list for a while, because it's got momentum. I mean, there's papers that were written in it. There's software that uses it. But basically, Yoshua Bengio is sort of the main guy behind it. He just sort of said, why am I spending all my time writing low-level compute graph code when there are Fortune 500 companies pouring millions and millions of dollars into it? So that one's there. Deep learning for J. If you're a Java coder and you really like Java and you want to do deep learning in Java, deep learning for J is a very viable option. They're a startup company. I've met their founder at a conference once. And then Baidu is paddle, so the big Google of China, if I'm even describing them correctly. And then PyTorch. So PyTorch is a very, very new one, and the rate at which it's already a number 9 means it is probably a pretty big contender. What's very cool about Torch is it has a nice, easy to learn interface to deep learning. If you want to do TensorFlow straight up and not use Keras, then you're programming compute graphs. And it's not the end of the world, but you'll definitely spend more time doing it. Keras, the idea of Keras was to use a Torch-like framework and allow you to use either TensorFlow, MXNet, or Thano as your backend. So Keras doesn't do the low-level stuff. They call out to usually TensorFlow, but also Thano and others. Oh, and I might have skipped CNTK. That's Microsoft's. Extremely fast. Pretty good general sort of one. So that is kind of a wrap-up of those. By the way, TF-Learn, just to show you how quickly things change, TF-Learn used to be around number 2 or number 3. And the first semester that I taught this class, which was only about a year and a half ago, that is what we used. So if you look at some of there's a few solutions floating around the internet. I know people always do that. I know fraternities and sororities keep files, but this stuff changes so fast. Every now and then I have somebody turn in an old assignment of mine in TF-Learn, because basically it was from the very first semester that this was taught. But that shows you how literally quickly things can rise and fall. TF-Learn was just notorious for breaking changes. I had to literally freeze and say, okay, everybody, do not install a new version of TensorFlow or nothing will work. And then I would probably spend 2 days updating all my examples for the next. They just could not. They had a lot of really smart people working for them who all pulled it in different directions, and lots of breaking changes. And if you're not familiar with that term in software, a breaking change is when you upgrade your software to, like, maybe you install the latest version of Java, and things in your old source code that used to work on the old version now don't work because you have to update them to the latest version. They can be annoying for software. Cafe2, dlib, I have no idea what those are. And NVIDIA digits, that's sort of their own spin on this. I've not worked with NVIDIA digits. So the thing to definitely for a neural network, be familiar with the structure of it. Neural networks have an input layer, multiple hidden layers. You can have hundreds of hidden layers if you use ResNets or other types. We'll see a ResNet later in this semester. Another important part of neural networks that I've seen people, even at my own company, like to ask about on technical interviews is bias neurons, and what are they really for, and why do you have them? They're essentially the y-intercept of neural networks. And I have a slide that shows you sort of what they do and why they're really needed there. But they're not inputs. You can think of them like an input that's always 1. The weights of the biases are what change to give them their effect that they have on the neural network. And you have biases on all layers except for the output. You wouldn't want a bias on the output because it would have nothing to connect to. And then I don't show it on this diagram, but we get to it later. There's also context neurons. So context neurons are used in recurrent neural networks. So LSTMs, GRUs, those kind of things. We'll see more about that later. Neural network calculation is important. So this is how you calculate a neural network. Lots of more theoretical machine learning classes, you'll program one of these. You'll program a neural network from scratch and then do gradient descent to train it. But we don't do that. We use TensorFlow for that. But the way that you calculate a neural network is it has any number of inputs, input 1, input 2, input 3. And then there's weights 1, 2, and 3. So every input into it has a weight. Now you may wonder where the bias neuron is. Did I forget to draw that on this one? The bias neuron is just an input like anything else. If I wanted to make this have a bias, I would simply set that input to be 1, and I would never let the user actually feed a value into it. So this little structure that you have here of inputs and the neuron, and then you always have an activation function. We'll see what that is in a moment. And that's the formula for how it's calculated. Theta are the weights. X is the inputs. Essentially, you multiply each weight by its input. You sum them all together. So you sum that weighted sum past that one single value through the activation function, and that's the output. And it's quite recursive. So that previous diagram I had, basically, if you think of this N1 as the output, these 3 inputs to it, just the arrows going to N1, so that arrow, and that arrow, that same structure just repeats itself over and over and over again across the whole feed-forward neural network. So to calculate this whole thing, you would calculate this one by multiplying that weight times that weight times that weight times 1, so just add it to it. Then you'd calculate this one. You don't have to calculate the bias, it's essentially 1. The biases are all 1. And then you calculate this one using the values that you just got by calculating that layer. So that's the feed-forward process of it. So you hear feed-forward backpropagation neural network. Backpropagation is just using chain rule and gradient descent calculus, taking the derivative of this output neuron versus the error function. I do have an online example of this. Let's see if I can click this, and hopefully it won't. Yeah, that worked. So this is something that I wrote in JavaScript. And this basically lets you see that whole process go. So if you calculate for the input, so this neural network has 2 inputs. This is a neural network like you would train for an XOR operator, because if you're visualizing every calculation, you don't want a gigantic neural network. But this shows you literally the internals of how it works. If you want to, I know this page gets a lot of traffic and questions from people in more theoretical machine learning classes who have to implement this, because what's very good is they can check their code, because when you do calculate input, it gives you the output, and it gives you all the intermediate values. So if you're trying to check your code, if you're trying to write a neural network from scratch, all these calculations down here that I give you are quite useful for that. It also does the training, so if you train it, it also gives you all of the backpropagation. A lot more calculations for backpropagation than there is for just the feed-forward part. But you can see here, it literally, you can change any part of this that you want. You can change that weight to 35, that weight to, I don't know, 1. And then you can calculate the input, and that's 0.74 should change. Yeah, so 0.717. JavaScript is a great little language for writing these sort of interactive applications. I don't have to worry about, do you have the right version of TensorFlow installed, or I should probably expand this too. Otherwise, people on YouTube comments will be telling me, why did you not expand that? So, and then you can also randomize the weights. So I have several of these if you want to see various training algorithms and just watch them step through. So if you really truly do want to know exactly what is going on under the neural network, this is it. A common question that I get that is just not that there's no real good answer to is students will ask me in particular, okay, so after you've trained it, what is the hidden 1 neuron doing? Or what is the hidden 2 neuron? Or how do you know what each of those neurons are doing? And really, you don't. They're very complicated mathematical models to train. There are algorithms that you can run that will look into the neural network and give you reports on what some of the internal structure actually means. But by and large, it's sort of a black box model. When we get to the convolution networks, we will see that you can visualize some of the edges and other things that the neural network is visualizing. Another thing that you can do that's very interesting is you can find interactions. So an interaction is when 2 inputs to the model affect it together. So if you, like on the miles per gallon data set that I give you, that we use a number of times, the cylinders and the size of the engine are very much interacted together. So just the number of cylinders in a car doesn't mean all that much, because you need to know how big each of them are, and that's what the displacement of the vehicle will tell you. So you can spot interactions very often by having inputs that have very strong weights. So if you have, say, a hidden neuron here and you see very strong weights to 2 of the inputs, that's usually an interaction that the neural network has discovered in some way, shape, or form. The Titanic data set is a very common one, and interactions are present there. So the Titanic, when the ship sank, the most important predictor on if you're surviving or not is your gender. Males didn't make it off so well, females did. But if the second most important one, that's an interaction, because it depends. If you're a male, the second most important term or predictor is your age. If you're a female on the Titanic, the second most important predictor is your ticket class. So neurons will get assigned to dealing with those different sort of combinations, and you can extract those out of the neural network. One really cool algorithm that I've seen, it's implemented in a commercial product. If you want to see automated machine learning, there's a product called Data Robot. We use them some, but what it actually does that's fairly interesting is it analyzes a complex model, uses the model like a neural network to tell it where all the interactions are, and then it builds those interaction terms, and it can do very powerful things than just with linear regression. The reason is certain industries like mine, for certain things, you can only use linear regression. You cannot use a big complicated neural network. So what we do is we cheat, sort of. Not really cheating, it's legal. To adhere to that, okay, you want a linear regression? Well, we run the algorithm, we discover all those interaction terms, and maybe there was only 10 inputs into the original model. We create 100 interaction terms engineered from a neural network, and yeah, it's a linear regression, but it also has all of those interaction terms in there. So that's a useful algorithm you can use. By the way, if you go to the parent page on this, I do have a number of JavaScript functions that I've written that let you peer into various processes for neural networks if you want to see how they work. Yes?
So is there times then where it's more useful to have more of those hidden layers to deal with possible interaction?
If the interactions are very, very deep, then yes, the more hidden layers. I wouldn't say the more the better, because you start to get really bad training times. And if you have a fairly simple data set and you just throw hidden layers on there like crazy, you're giving your neural network all the material it needs to overfit, which can be bad. Then you want to use dropout or some regularization, which we'll learn about later in the semester. Okay, so transfer functions, or activation functions as they're called, or sometimes even nonlinearities. There used to be a whole bunch of these. There used to be, well, they're still around. I mean, there's the sigmoidal one, there's the hyperbolic tangent. There were several versions of those two that were just more computationally efficient. But then one of the foundational sort of technologies of deep learning was the rectified linear unit. And the rectified linear unit is largely, not completely though, surpassed most of those, especially the hyperbolic tangent and the sigmoid. And by the way, hyperbolic tangent has a function in trigonometry. I haven't used it for that function since high school, but it does have a really good function for it. The reason you use it in machine learning is the shape. If you plot a hyperbolic tangent, it has this nice S shape, sometimes called a sigmoidal shape, that kind of squashes values between it, and it spans between -1 and +1. The sigmoid function looks almost just like it, but it's not quite. I mean, rather than shifting, you could easily just shift the hyperbolic tangent. They use the logistic function, which has been around in statistics forever. It's the same S shape, it's just between 0 and 1. But these days, you mostly use rectified linear units, and it depends on what, and there's several forms. There's leaky rectified linear units. There's a whole lot of research of, ReLU is now a family of activation functions. But what you want to use is the, if you're dealing with a hidden layer, you're most likely going to have a rectified linear unit. That used to be tangent or sigmoid. If you're dealing with the output, and by the way, inputs don't have activation functions. If you're dealing with the output layer, that depends on if you're doing classification or regression. If you're doing regression, it's going to be linear. If you're doing classification, it's going to be softmax. And softmax, I have an example of that too on the JavaScript page. You can plug values into the softmax function and see what it looks like. But softmax, all it does is, so if you're trying to classify something like the iris data set that I showed you, you have 3 irises, so there's 3 output neurons. Whichever output neuron gives you the largest value, that's the iris that you pick. That's how a neural network classifies something. Whatever output neuron has the largest value, that's what it's classifying. So if you just have three irises like that, it's pretty simple. The problem is, in statistics, we like for the outputs to sum to 1, because then they're probabilities. I would like to know the probability that the third iris is actually the iris that it is. I don't want to know that the third iris had 17 as the output and the other two had 3 and 1. I would like to turn those into a probability. So if you turn it into a probability, you'll see something like 0.7 or 0.9 probability that it's the one, and 0.1 for the other, and maybe 0.9, 0.01 and 0.09 for the others. So those are the things and there is also a hard max. The hard max is just literally basically summing all of the outputs and then dividing each of them by that summation. It doesn't use the natural logarithm, so it's a lot more harsh of a transition, which usually you don't want to do. You don't want to use hard max. It's not even a default option on TensorFlow. You'd have to code it yourself. So why is the rectified linear unit so much better than the other ones? You might have heard of a term. This is another apparently common, just introductory interview question. What is the vanishing gradient problem? And the vanishing gradient problem is basically you're taking the partial derivative of each of your hidden, of the error with respect to each of your hidden, or each of your weights. Once those weights go, once that gradient, the derivative goes to 0, it's stuck in a local minimum. It's not going to change because you're using a positive derivative to know that you need to decrease the weight and vice versa. But if it's 0, the weight's not going to change. So you tend, in the older neural networks, you tended to have large chunks of your weights just dying off. And that didn't matter. The other parts were still active, and you would prune those off usually at the end. But the rectified linear unit, if you look at what the derivative looks like, so here we see basically the sigmoid function. And the sigmoid function is S-shaped, just like I told you, between 0 and 1. If you look at the derivative of it, it saturates to 0. So in the older neural networks, you'd really try to keep those weights right in that area so that you don't have, I mean, they solved it in various ways. There's the flat spot problem that they used to have, they would call it, and then also just the vanishing gradient. The rectified linear unit is very linear. It is just the max of 0 and x. And the derivative of it, they basically make it 0 or 1 depending on if x is greater than 0 or less than or equal to 0. Technically, this is not differentiable at 0. They kind of cheat and just, but it's the definition of that derivative. So that doesn't saturate off to 0. So this really does a lot to eliminating the vanishing gradient problem. But if somebody asked me to define the vanishing gradient problem very, very simply, I would just say that the derivative of the weights sort of converges to 0, and there's no escape for it. Once they're at 0, in classic backpropagation, they could not, that weight is now dead. Okay, I will go ahead and pass this around. It'll end up somewhere in the back row, so make sure to return that to me. And then why are bias neurons needed? This almost goes all the way back to college algebra 101. But if you think of the weight as the slope and the bias as the intercept, that's pretty much what's going on. So if this is just a little program I wrote in R, but I basically changed the bias to various values, and you can see it's just shifting the entire curve to the left and to the right. If I change the weight, you can see that it's basically just bending it. Also, since we're multiplying the inputs times the weights, if you didn't have a bias, it would be very hard to deal with zero input. So if your input is 0, that's going to multiply, that's going to cancel out all your weights. And it would be very hard to return anything but 0 in that case. So when your inputs are all 0, that's when the bias really comes out. And then just the code for Keras. So you've seen this probably over and over if you've done, you see this in assignment 4. But we're just creating a sequential model in Keras, which we use a lot in this class. There's other models you can use as well. But I create basically a dense layer. Dense layer just means everything is connected to everything. At this point in the class, everything is dense. There are always dense layers. But later on, we get about 2 or 3 more layer types when we start to do LSTMs and seeing how to apply this to natural language processing and other things. Since this is regression, usually you will have one output neuron, so one final one. However, this is the flexibility of neural networks, and this really is difficult to accomplish in other models like support vector machines and whatnot. But your output neurons, you can be both classification and regression at the same time quite easily. You just have one output regression neuron and then maybe, I don't know, 8 other neurons that are the classification part. So you can be in both worlds at the same time. You can also, they use this a lot in robotics, you can also regress. You can have multiple outputs, so you can have multiple output regression. Normally when you do a regression, you're predicting something like miles per gallon. But you could restructure that data set and basically have 2 output neurons and try to predict both the miles per gallon, I don't know, and the displacement for a car. It's part of the reason we use relatively simple data sets going in. I can give you examples related to the data set that you've already seen and when you do that. We also deal with something for images called an autoencoder. There you will definitely have multiple outputs. That's how you teach the neural network to compress data. And then finally you fit it. Verbose is how much status information you want, and epochs is how long you want to train it for. All right, and then the next one with my stock photography. Module 4, training a neural network. Thought it'd be good. Wrong season of Olympics, but. So backpropagation, and here's some interesting things on backpropagation. So backpropagation was, as far as who invented it, several people, some attribute it to, Hinton did some early stuff with it, but I can't think of his first name, but Dr. Wurbos, I actually met him at a conference in Alaska, so interesting guy. So it's like, wow, there's the guy who he used it for his PhD thesis a long time ago, and the early neural networks, they had no way to train them. They just set the weights up by hand. So very often, if you take a class in machine learning, they will give you some logic problem like A or B, not C, whatever, and they tell you to just turn that into a neural network. And you can. You just have to know what the weights are for an and, what the weights are for an or, what the weights are for a not. And you just build up the whole logic gate. But backpropagation, what's very interesting about that is just about every training algorithm in neural networks somehow goes back to backpropagation. There are other ways you can train it, but backpropagation is just darn efficient when you do it correctly. You can use simulated annealing, or you can even just throw random numbers at the weights and just keep the best combination. It's a random walk. it's on a small one, it's amazing how well that actually does work. But there's been a few articles coming out that are kind of interesting. Jeffrey Hinton, he's pretty much at the top of the food chain of neural networks, so he can say things like, maybe backpropagation is the wrong idea. Maybe we should pretty much reboot neural network training from scratch. I gave you a link to his article. It's pretty good. And then another thing that an MIT article talks about is AI riding a one-trick pony, and also harkening back to backpropagation. That is very much the holy grail of AI, is the general artificial intelligence. Basically one model that sort of does everything. I mean, you've got things like Watson. Watson could read a book on chess or could read a book on Go, and it could have a nice conversation with you on chess or Go, but it couldn't actually play it, or at least not at this point, from what I've seen on that. Marketing people also like to make big statements, like I remember when they were talking about Watson going to medical school. So going to medical school is a pretty major endeavor. So when they say, okay, a computer is going to medical school, it's like, yeah, not really, but sort of. We were talking to some of the IBM Watson people, and we wanted to apply their data set in a country where Spanish was the primary language, and we were told by IBM, oh, Watson doesn't support Spanish yet. It will probably take us about a year to program that. And our question then was, okay, so Watson can go through medical school, which a fraction of the population could probably do, but learn a second language, like you could do in a high school class, eluded it. So that kind of did not make sense. Now they've since gotten Watson a lot better at picking up other languages completely on its own, but the different techniques are sort of one-trick ponies. You can't just use one right into another. They're very much seeking the general artificial intelligence, and deep learning is probably coming closer than many of them. But that's when we'll have the singularity. Thank you. Another important thing is just building the feature vector, learning how to deal with different types of data. So character data, you can really think this is more to statistics, although most statisticians, when you mention this in coding, will point out that the guy who came up with this, who I cite in the paper, was actually, I think, a political science major, I forget, but it is kind of interesting. You like character data. Either it's nominal or it's ordinal. Nominal just has no order whatsoever. That's where you use dummy variables. You like the three irises. There's no order to those three irises. They're just plants. Or if you had, I don't know, if you were classifying office items like a mouse or other items. There's just no particular order to it. Ordinal is when you can put things in an order. Like if you had tall, venti, and grande, like at Starbucks. Even though you would have the words tall, venti, and grande, don't create three dummy variables for that. You want to basically, most primitive would just be to say, okay, tall is going to be 0, venti is 1, and grande is 2. But that assumes a nice linear progression of those. The better would be to put the fluid volume in there or something such as that. So always try to convert things into numbers if at all possible. Like colors, convert it into RGB or hue saturation, some of the more natural color encodings. Numeric data. This is somewhat interesting. I mean, you have interval and ratio data. Usually this does not make a difference to how you encode it. Interval data, you have no defined start. And how you can always tell interval data is like a temperature. You would never say yesterday was twice as hot as today. You can say that one car is going, unless you're dealing in Kelvin, but then you could say it. But you could say one car is going twice as fast as another. If one car is going 20 miles per hour and another car is going 40 miles an hour, that second one is truly going twice as fast. If it was 10 degrees Fahrenheit or centigrade, it doesn't matter, yesterday and 20 today, it's not twice as hot as it was yesterday, because you have to have that sort of zero starting point for that sort of comparison to make sense. So is it ratio or is it interval? And then different data types. So like, be careful of things like zip codes. They look like numbers, but they are not. Lots of things in my field with medical records look like numbers, but they're not. So you have to be careful with that. Street addresses are very non-numeric. They're very difficult to encode unless you use some third-party database. We'll often convert street addresses into latitudes and longitudes. And just latitude and longitude alone is pretty good, but sometimes we will use another latitude, longitude, and do almost like a K nearest neighbor, and we'll say, how far is this address from the nearest city center? Kind of an urban measure. That's something that we have done quite often. Unstructured data, or like drug names, that's very difficult. If you look at the drug encoding that we use in the United States, that we get a lot of our medical records in, there's just too many of them. I think there's around 75,000 currently. So that would be a deep neural network can definitely handle that, but you want to try to put those into hierarchies, groups and families of drugs. Because the problem is, with 75,000 drugs, those incidences are going to be nice and normally distributed. So some of those drugs are just not going to come up very often. And that's one thing that's very difficult in training a neural network or training any machine learning models, is when you've got multiple inputs. So a neural network might learn very easily that a BMI of low 20s is quite good, 30s and above not as good, but it might not ever see somebody with a BMI of 5, and it might just pick up on, as that decreases, it gets better. So anytime you have data coming in outside of the sort of high-dimensional cloud of where your input data came from, your model, like a neural network, is now extrapolating, and that can be dangerous. Unstructured data is very difficult, like XML documents. We actually harvest data out of Wikipedia. Wikipedia has all kinds of data. It has drug codes in it, so you can get all kinds of interesting data there. And then the stuff that neural networks are really, really good for in the world of deep learning is time series, audio, and video data. We'll see some of that later. This is a good example of where encoding locations can be valuable. I was fairly disappointed with a data set that I got a hold of. The life insurance industry, there's several big sort of problems that they're working on that they're really interested in getting a model for. One of them is, does somebody smoke or not? Because when we're classifying mortality, that's up there in terms of what we're going to charge you and who we want to market to. So if we can scan a mailing list and cut out people who are smoking, not that we won't give them life insurance, we'd be glad to give them life insurance if they apply, but maybe we're marketing a product that is more at the higher, the more desirable risks, we'll want to target just at them. Well, I augmented my data set with a marketing data set and was looking for which values were the most predictive. And I noticed that I had forgotten to take out latitude and longitude. Normally I would have probably removed those, and I found that they were among the most predictive inputs. And that showed how horrible my other predictors were. But if you look at this map of the United States, it shows where smoking is more common. So you can see California, not so much at all. If you look at Kentucky, West Virginia, the coal belt, much more prevalent. So very common, I guess, among minors. Another big indicator of it is certain cities will just outlaw it in public places. That does have a definite correlation. The causation is a little more difficult to figure out, but the correlation, it definitely pulls it down. And by the way, if you're not familiar with those two terms, correlation and causation, that just means, correlate just means when something happens, we notice something else happens. The perfect example of where correlation is not the cause is if you look at a graph for when people die of drowning, it kind of bumps up and then goes back down. If you look at a similar graph of ice cream sales, it follows exactly the same thing. So if you didn't know your statistics well, you would say that consumption of ice cream encourages drowning. The reality is ice cream is sold more in the summer. People swim more in the summer. It's a spurious correlation, so you don't want to do that. But the U.S. government picked up on another spurious correlation and ran all kinds of videos on ice cream causing polio. Ice cream doesn't cause polio, but polio, due to other biological reasons that I am not qualified to completely understand, spikes up in the summertime, just like drowning. So there was all kinds of public service announcements and other things of don't let your children eat ice cream until, I don't know, they're 10 years old and safe. You can Google it on, or you can look it up on YouTube. There's all sorts of, there's a book called Freakonomics that has all sorts of those in there that's somewhat interesting. But anyway, the point is, don't discount location. Location can be quite predictive. There's definitely not just random variance in this map that you're seeing here. Overfitting is very important. So when you pick how many epochs you want to train your neural network for, you basically you don't want to just train it forever and ever and ever, because your training is going to tend to go lower and lower and lower and lower. Very rarely, if you overtrain, would you see your training ever spike up. It's just going to asymptotically kind of converge to zero. But if you hold out data that is separate, then you're going to basically start to not do as well. The comparison that I like to give on this is if you've ever taken IT certification exams, so like to become a Java certified software developer, or some of the actuarial exams have this, they'll give you a practice exam. And that practice exam, you can keep taking it over and over and over again, and you'll keep doing better and better and better on the practice exam. Maybe you're even getting 100% after you've taken it about 50 times. But then when you go to take the real one, you'll fail because you're overfit. You've been focusing on this little training data that you had, which is the practice exam, and not learning really anything. So neural networks are susceptible to that. And overfitting is the problem. Early stopping is probably the easiest way to combat overfitting. We have examples of other ways to do that, and they are basically, this is how you do it. So you have your data set, you split it into 80-20, so this is an 80-20 split. 75-25 is also very common. You fit your model on your training data, and then you finally evaluate it at the end on your validation data. And it will usually always be doing better on training data than it is on validation data. So this is a very, very important concept. Cross-validation takes this even further. The problem with early stopping on just a training and validation set is this validation data never gets a chance to train the neural network. So you're throwing away training data that you might have used. So what you do is you tell your neural network to train. So often you'll see number of epochs. I'll put like 10,000. Heck, I could put 1,000,000 because it's going to stop as soon as that validation no longer improves. And then one other thing that's important, you'll see several examples, and I want to explain this, what's going on here, because I don't always use this. You'll see where I use the check pointer, and I mentioned this in the class notes, but early stopping and getting the absolute best weights. So if we go back to this one, and you're sliding down this curve, and now it starts to diverge. Well, there's a parameter you give called patience. And patience is how far you'll let it get down here before you say, okay, validation is no longer improving. It's done. I'm going to stop training. Well, what weights do you want? You don't want the weights right here where patience finally gave up. You want the weights from back here. But to do that, you have to put some extra lines of code in there. And on small data sets, it doesn't really matter. So I don't always grab the absolute best. The absolute best weights would have been right here. Sometimes I'll grab it off when patience ran out because, by the way, this is a very exaggerated graph. It usually doesn't spike up quite like that. What often happens is this just goes down and then sort of levels out, and it continues this way while training goes down further. But if you truly want the absolute best weights, and do this more on bigger data sets, what you do is you use this check pointer that you have in red here, and that file path, bestweights.hdf5, that is just a file format, a binary file format. It saves the weights every time there's a new best set. And then at the end, you load those weights back. Because otherwise, the weights, this model fit, you're just going to get the weights from whenever it gave up and stopped. So that's very important if you're trying to pull out the absolute best accuracy possible. Like a Kaggle competition, or just a model we're creating, like my day job. We'll always do this kind of thing to get the absolute best weights. If you're just testing things, for any of the assignments, you really do not need to do this. For small data sets, you can actually sometimes get a rather annoying error, because what happens is this is all multi-threaded code. You can be saving that weight. It can be still saving that weight when you try to load it, and you get a file sharing error. That would never happen on a large data set, but like the iris and the miles per gallon, yeah, you can definitely run into that. So that's why a lot of the examples don't use that. But if you truly want the best weights, that's what you want to do, the most accurate. And then, let's see, evaluating results, root mean square. So if you're using regression, you'll use root mean square. If you're doing classification, you want to use accuracy or log loss. There's about 20 some odd other ways that you can measure this. But these are the most common, and these are the three that we use in class. Root mean square, what's good about that is it's in the same units. So if you train the miles per gallon data set down and you have a 3 root mean square, that means it's off by about plus or minus 3 on the miles per gallon. So root mean square, since that's in the units, if you had tried to predict the price of a car, plus or minus 3 would be pretty darn good, $3. Classification is just your accuracy. Accuracy is just, it's like an exam. Did you get 90% of it correct, 95% of it? Log loss, you don't want to ever report that to a business user or somebody who's not a data scientist or not. is it's a very strange sort of number to read. Usually around 0.3 or 0.2 is relatively good, but whole number 2 or whole number 3 is really, really bad. You won't see much worse than that. But it's another form of evaluating it. What's good about log loss is it punishes neural networks that are confidently incorrect. So if it was incorrect on something and it was very confident, it'll get an error. Okay, and then cross-validation. Let's see, cross-validation. Last thing we'll look at, then we'll take the break. Cross-validation is simply the this lets you get by with not having. This lets you use your entire training set. So you divide it into 5 folds. The thing to remember about cross-validation is you are going to end up with 5 different neural networks if you do a 5-fold. Because you will literally take your data set and each of these folds, so if you have 5 folds, each of these sets, fold 1 gets to be the validation set. They take turns being the validation set. And that is cross-validation. So you'll use that in a subsequent homework. So definitely you'll get to see the code to set it up. Okay, and then classification and regression, I will go through that after the break. And then we'll also have some time if people have individual questions for me. But we'll take a 10-minute break. I will resume at about 7:13. All right, we'll go ahead and continue. So classification and regression. Those are like your two, probably in neural and machine learning in general, there's 2 sort of fundamental classes of learning. There's supervised and unsupervised. We do both in this class. So far we've been doing only supervised, but we'll get to some unsupervised as well. Unsupervised is when you don't have an outcome. You don't have anything that there's no why. And then there's also classification and regression. So I've seen on certain interviews, either I've asked the question or one of my colleagues, that's a real quick, just kind of weed out question on if we're talking to potential like data scientists, we're phone screening them for internships and other things like that. What's the difference between classification and regression? If you don't know that, you've probably not done a lot of machine learning or modeling. Classification just means you're trying to classify something that's not numeric. So like that, the fruit that I have sitting there, that is, if you're trying to classify if something is an orange or an apple or a kiwi, that is classification. Or to use my industry as an example, life insurance, maybe a risk class, super preferred, although those are sort of a continuum, but they do sort of branch off because you have super preferred and you have super preferred non-smoker and just different sort of, so it's not just a straight linear progression necessarily. Regression is numbers like financial symbols and kilometers per hour type things. The way you set these up as neural networks is just your number of outputs. So I'm using a life insurance example here. I am doing maximum face amount. So what's the maximum amount of money that we would insure somebody for? Maybe 250,000, maybe 500,000, maybe I think 50,000, however low the particular product type would go. And then you also you can divide them into different risk types, so preferred, standard, substandard, or decline. You could also treat that right one, classification, you would just do a risk score and kind of bucket it into the correct one. But this is an example of a classification. So you basically have one output neuron for each of your classes. And then you use softmax to make sure that they all sum to 1, so that they're probabilities. Confusion matrix is a really good visualization. So the reason I'm showing you kind of some of these visualization types is you want to be able to explain them. So the confusion matrix, this is for classification. A good model will always have a very well-defined diagonal. So this one's doing it really quite well. It is misclassifying a few, but there's not enough of them to really be able to tell. So what this is telling you is, yeah, if you can see my mouse pointer. Okay, it tends to take it away if I don't move. So iris setosa, this is what it truly was. So this blue is telling me the count of how many iris setosas it truly was, and it was also predicted to be iris setosa. So the true label was setosa, and then the neural network also predicted setosa. That's good. If you saw some blue out here, that would mean it was frequently misclassifying the Virginica. So you always look for the straight diagonal, and then each of these boxes is essentially just the pairwise sort of, does it confuse something for another? So in life insurance, if we saw that it was frequently confusing super preferred for super preferred non-smoker, it would mean it's not detecting smoking. And these can be very valuable, and the top and bottom are not duplicates of each other. So there's no symmetry here. Because it could be that you confuse iris setosa for iris versicolor, but not necessarily the other way around. So that's a confusion matrix, only used in classification. You don't use them in regression. There's also an ROC chart. ROC stands for receiver or operator characteristic. It's really more of a double E, electrical engineering term. But this is good for a binary classification network. Because what you do, this is used a lot in medical tests. You have to deal with false positives and false negatives. Sometimes false positives are better, sometimes false negatives are better. Like if you're trying to predict if a bridge is going to collapse, the positive would be collapse. Which is better? Do you worry about bothering an engineer to go out and check it? Or do you worry about, we'll just let it collapse. That way we won't bother the engineers as much. So false positives and false negatives are not always the same. Like in credit reporting, very often, if you're going to make a mistake, sometimes the credit bureau would rather fail to issue a card to a good risk than accept a bad one. So the point is, you set, and I have a whole sort of description of this, but you set your threshold wherever you want it to cut off to balance it more towards false positives or false negatives. The way to read one of these charts, ROC chart, is if this line, so if the line on your ROC chart is straight like this, that's a model that might as well be flipping a coin. It has no predictive power. As this goes higher and higher and higher, it is more and more accurate of a model. You can sometimes see this line tuck in and go this direction. That means you're less accurate even than a coin toss. And that can be, because very often your sample data are weighted incorrectly. If you're trying to predict that a person you randomly run into at a school is male or female, that's going to probably be about 50-50. But if you go to an all-girls school or an all-boys school, it's going to be more like 95, because you might run into somebody of the opposite gender who works for the institution. So if you're flipping a coin to determine that, you could just always say male or always say female, and you would be more correct than the coin toss. So always be aware of that too. If you have highly unbalanced data, that makes it very challenging to predict. So on our smoker models, smoking in the United States, I think on average is in the teens. So if you wanted to just do the lazy model, you just always say no, not a smoker. And you'll get probably around 76% accuracy. But that's not good because the data are so unbalanced. And then there's the lift chart. Lift chart is very common in regression. This is a bad lift chart because basically the blue and the orange are not close together. What you do for this, and this is not predicting something over time, so the mathematical term for this line would be monotone, meaning it's monotonically increasing. It always increases, it never goes back on itself. So if we were doing the miles per gallon one, I would take all the miles per gallon and I would sort them from the highest miles per gallon to the lowest, and that would be my blue line. And then for each of those individual ones, I would get the neural network's prediction, and I would put the orange at where it had predicted. So I don't sort the oranges, I just line them up to the in order expected values. And what this lets me know is, so if I was analyzing this one, first of all, I would realize, okay, this is not a good model. This is a really bad model, but because it's up and down. You want to look for things like, is it consistently above? Is it consistently above, but then maybe we hit here and now it's consistently below? You look at those kind of things to try to figure out how to represent the data better so that the neural network can predict. So I noticed one where we were doing these actually by BMIs, and it was fairly accurate here, and then it tucked under and was inaccurate. What I realized is if you look at male and female BMIs, females typically on average have lower BMIs than males. It's just the structure of the body. So that crossover point was where the genders were diverging on that. I added another, I basically separated the BMIs into males and females, and then it was much more accurate. It didn't have that sort of crossover. So you look for these kind of things to help you tweak your data, and this is probably the hardest part of data science, is just looking at your outputs and really trying to tweak and re-represent your inputs so that, I mean, that's how when I compete in Kaggles, that's how and by the way, I mentioned Kaggles off and on. There's a whole little presentation on it because your first project is a Kaggle. Kaggle is like professional sports for data scientists. They put these competitions out there, and all the data scientists compete on them and try to get into the upper percentiles. And what I will do is I'll just look literally at my data where I'm right and where I'm wrong using my training, and I'll just look at, okay, why did it confuse that? And I'll try to engineer new features to help it pass those cases. And that's very time consuming. We'll get into that a little bit with the Kaggle. So we'll do a Kaggle in class. So it's a data set that I put out there that you will do your best to predict. And there's a few tricks to it that I'll talk about next time. Okay, so those are all of my slides. Let me just show you the assignments real quick. think I zipped by them. Oh, I didn't. Okay. So assignment 4, which is due tomorrow night, I assume most of you are well into that, but if you haven't, let me just explain it real quick, or if you're in the midst of it. I didn't pull how many submissions I have on this yet. But basically what I'm doing is I am giving you a data set. And by the way, all these data sets are generated by a program that I have. So some of these data sets, they exhibit certain characteristics. So we'll be talking about them later in class to show you kind of what the challenges were. But if you click on the data set and just look at it, so these are generated, but they're not just pure random numbers. There's some math going on behind here that make them quite predictable and exhibit certain issues. But the ID is just the ID field. You need to send that back to me. That way I know what your prediction is. So I know you're trying to predict ID1 or you're trying to predict ID2. Distance, height, landings, number. The name really doesn't mean anything. I mean, landings, it sounds like you're talking about maybe airplanes, but these are just random sort of generated values. The regions, so that's something you might think about dummy variables. You might think of something else. There's no real order to them, so that probably would not, converting them to ordinals would not necessarily help. And then target, I did have a few questions about that. What are we supposed to predict? Well, you're supposed target. Target is your target. So target is Y. And that's what, so you're trying to use all of these to predict. And by the way, ID is not predictive. And this is an issue that you run into in Kaggle competitions because there is an ID. And in some competitions, the ID is predictive. So if putting the ID in helps, that means in a Kaggle, that means that your company who is sponsoring your Kaggle messed up badly. So the order that these rows in might mean something. What happens, what would happen if, say I took the training set and sorted it by target. So it's in order by target. And then I assigned IDs. Well, if it's in order by target, and that means lower ID is probably a lower target. There's a correlation there now. And the technical term for that is target leak. You're leaking information from your target into the data set that you don't want to be there. In Kaggles, that's how teams get advantages over each other. They try to detect the target leak and exploit it. In my job, I don't want target leak. Target leak means I am leaking something into my data set that's making my model appear a lot better than it should have been. A data set that I'll give you an example of target leak from the real sort of world. We were trying to write a fraud detector. And I let somebody who, actually an intern, he learned, and he just had not done this a whole lot, and it's perfectly fine what he did. It's a way to let him learn more things about it, but he introduced a target leak by mistake. What we were doing is all of these claims, we had fraudulent or non-fraudulent, but there was another column called status, and that status would go to resolved. Resolved means we've already paid it. It's done. Resolved, you only get that status of resolved after. So the resolved would either go to paid, denied, or under investigation. When his model would be used was before we would ever even do that. We would always run it on pending. So somebody had just died, they had requested it. That resolved status occurs after we pay out. So it's a target leak. because every single one that was fraudulent almost was under investigation. The point is you don't know that. You want the model to be telling you that. So that's an example of real-world target leak. And we just removed it. He was also very excited that his model was returning an accuracy rate of about 98%. Be afraid of those. Usually your model is not going to be that accurate right out of the gate or ever. Be afraid of overfitting at that point. And there are a few missing values, so you need to deal with those as well. So what you do with this one is you take all that data, and in the assignment, I give you the helpful functions. You always want to use those. Those are the ones we talk about in class. And you'll want to submit it. I have seen that people have been using the submitter quite a bit, and that's good. That's entirely my intention. Because, and it does cause people to get better grades, but that's a good thing. Because I would frequently have people submit, and I would even tell people, the first thing I check is, do you have the right number of rows? And you always want to come up with a few kind of just basic checks like that. So I will tell you, my submitter will tell you if you don't have the right number of rows. And then I have a more advanced checker that actually is what results in your grade. So it's actually a deep neural network. It's my neural network teaching assistant. So, and all it does is it flags, basically, it says, yeah, I don't see any problem. It doesn't actually give you a grade. It'll just say, Jeff, you need to look at this one because I can't figure it out. And usually those are the ones that don't have a perfect score. It doesn't figure, then I figure it out. So, but most of them, it's able to say, yeah, that's fine. And it's very similar. That's what we do with our, we have a definitive decline model and a rapid, that's a big thing in the life insurance industry right now. You want these straight through processing. So you create a model that looks for your best insureds, and we don't even have to send them to the underwriter. The model just says, yep, they're good, move them on. So it's similar to my grading deep neural network. But it can look at the source code and actually see, okay, this should have been there, that should have been there. And if it flags yours, either it means you used a completely different technique than what I did, and that's fine if you get the right answer, or something's missing. So what you do for this one, you generate it, you get the IDs because you want to put those back in. If you don't know how to add columns to the to a data frame, it's covered in class 2, and I also answered a question related to that on Piazza, so you may want to look at that. But you're basically just returning, like I ask you up here, normalize all the numeric values to z-scores and text to dummies. Do not normalize the target. Your target is named target. I added that one after a few questions. If you find any NAs, replace them with the median value. No need to cross-validate. So just train the whole thing for 250 steps. You'll overfit, but that's okay. You'll get, if your warning is somewhere in that range, do not worry. If it says warning, the mean column prediction is different by 100, worry. If it says 25 even, perhaps worry. But below 5, not so much. And it's just a quick check. So any questions about that one? And I'll be available afterwards if you have individual questions too. Let's look at the next one. Whoops.
So,
oh yeah. Yes.
I think I have my data, but I think it's a formatting thing, and you had brought up the fact that I guess we had to add the IDs back.
Yes.
Because you provided a sample print function that kind of prints it out
right
in a certain way, but obviously you don't want that. You want like a CSV type.
Yeah, a CSV type thing.
So I'm assuming if I just add the ID column back to my results, that should.
You'll probably be in line then.
Okay.
But yeah. And if you're not, definitely feel free to email me a source code and I'll take a look. So, okay, and then the next assignment. And by the way, that's why I make assignments due the nights that we meet class tomorrow night, because, okay, it's, I mean, I'll be home by like 9 p.m., so I'm probably not going to answer any any questions between now and 11:59 p.m., but I will answer any questions that pop in tomorrow. Okay, so let's look. So that was 4. Let's look at 5. 5 is very, very similar to that, but now you're putting in k-fold cross-validation. You might get less accuracy here because the k-fold is going to prevent you from overfitting, and that might look, you might not get as good of a validation score, but you can see if you're, and by the way, my solution files that it's comparing you against, I don't do anything extreme. I write this basically just using the stuff that you've learned up to this point. So you should be pretty close in line with mine. Again, you're predicting target, replace any NAs, use a 5-fold validation. There's sample code of using a 5-fold validation. You'll want to start with that, modify it into it. Make sure you use the right data set. And I make you do a little bit of column math, but they talk about that. I mean, I talk about that in, I think module 2. So you'll get the Y. Y is literally straight from the training set. That's what it should have been. Prediction is what you predicted it to be. So in an ideal model, those two would be the same. Diff is just the difference between those two. So that is, and I do point out that your RMSE will not be as good. We'll get into why when we get more into regularization and overfitting. So this is a k-fold cross-validation. And then the last one that is due before, let's see, 4, 5, 6. And this is just a classification neural network, so now we're trying to classify. So that's like individual items, like you're classifying the irises, or you're classifying an apple, pear, orange. It's not a number. And I just tell you all the usual sort of things. Here you don't have to calculate a difference. You're just giving me the ID, the Y, and the prediction. Okay, and like I said, all of these have the helpful functions and the sample code just to get you started. And by the way, the data frame, it's essentially a CSV in memory. I mean, if you ever want to see it and look at it in Excel, just do that, and then you'll have your CSV file. The reason I have these in here is this is literally exactly how I generated my master files that it compares you against. I wrote it, I filled in the code that is your assignment, and then I wrote this, and there's 10 of those, so there's 1 through 10.csv, and they're uploaded in my... You'll see a little bit about how you deploy a neural network, so how you let others actually use it. This web service that you're posting these to, this is actually running in Amazon AWS. So I actually upload all of these into Amazon S3, and it uses something called Amazon Lambda but I will show you how to actually do that. So if you created the greatest non-smoker model in the world and you wanted to put it up in a web service and charge people to send data and get it, that's I'll show you a way that you can do that. Okay, that is really all I had. The next class session is on the syllabus. I don't remember the exact date. but it's in a couple of weeks, and we'll see you'll get to start on your first project. For those of you working ahead, I will probably post the Kaggle information in a couple of days, but I don't really expect anybody will start on it until next class session. All right, if you have individual questions for me, I will be here as long as need be.